Hello, AP Chemistry 12. This is Mr. Chan. And what I wanted to do today was I wanted to finish off electrolysis. And what I wanted to do was focus on the type 3 cells. Now, it is like a type 2 cell, but now the electrodes can participate in the reaction. Now, recall in type 2 cell, what you have is you have inert electrodes. So what you were focused on is you were focused on the oxidation or reduction of the ions in the solution. So in this particular case, it was copper 2+ ions or sulfate 2-, and you had to consider water. Now, if you take a look at type 3 cells, what happens is the electrodes can now participate in the reaction. Now, the three most common type 3 cells is electroplating, electrorefining, and electrowinning. Now, for electroplating, what happens is that it's an application of a protective coating on a piece of metal. So, for example, silver on a spoon. Okay, now, so what happens is at the anode, you have, in this case, the metal you want to coat with. So in this case, let's say it's silver, and the cathode is the object you want coated. So here, the cathode, it's the object coated. Okay. Now, so what happens in this case? So for silver, because it is directly connected to the battery, what happens is that it will tend to oxidize. So in this case, the metal oxidizes. And what happens is that it produces, in this case, silver ions. So you can see in the diagram, silver ions are produced. Now, the silver ions are then electrostatically attracted towards the cathode. And then what you get is you get metal that is coated on this particular spoon. Okay, so what you have is you have your metal coating. Now, what's the significance of making sure that the metal on the anode is the same as the metal solution? Well, there's two reasons. Number one is if you take a look at your standard reduction potential table, what you notice is that silver is better at attracting electrons than water. So by putting the silver as the anode, what you do is you keep the silver ions at a constant concentration so that it will continue to be coated on your cathode. All right. If the concentration goes down, then what happens is the ability for silver to reduce starts to go down. And then that's when you start getting unwanted side reactions. So that's the one reason why you want to make sure that the metal and the solution should be the same ion. So metal and metal ion should be the same. Now, you might say, well, Mr. Chan, what if we put instead of silver, let's say, you know what, I made an oopsie and I put a piece of copper. So now in this case, what you get is you have copper +2 ions. Now, so how will that work is now you have a mixture of copper and silver. So initially, if we look at the standard reduction potential table, silver will still undergo reduction because it has a higher reduction potential. But as the silver ion concentration starts to go down, what happens is copper will then become the predominant reaction. And so what you get is in this case, instead of pure silver, what you get is you will get maybe eventually a mix of silver and then copper. So that's why it's important for the anode and the metal ion in the solution, in this case, silver ions and silver metal, to be exactly the same. Okay. Now, the other one is electrorefining. So what is electrorefining is obtaining a pure metal from an impure sample. Now, so what happens is what you have is at the cathode, you have your, it's almost like electroplating. What you have is you have your pure, let's say in this case, copper. So what you do is you set a voltage so that what happens is the copper ions will undergo oxidation. So in this case, both the zinc, nickel, iron, and copper will undergo oxidation. But what you do is you set a voltage so that the copper ion is the one that will get reduced through electrostatics. Now, what happens is you will notice that there's metals like tellurium, silver, and gold. What happens is this becomes the sludge. Now, for some refining companies, the sludge is actually quite valuable because of the fact that there is silver and gold in it, and that can be extracted by another process. Okay, so that is what we call electrorefining. The last one is electrowinning, is where a process where a pure metal is obtained from its ore that has been put into a solution or liquefied. One of them is aluminum production. Now, for aluminum production, what they do is they take aluminum ore, they dissolve it into this thing called alumina and cryolite. What happens is that dissolves the alumina or the aluminum oxide, and through electrolysis, what happens is you get pure aluminum that is refined. Okay, now those are the three types. The one that you'll probably need to focus mainly on will probably be electroplating. So my recommendation is for you, when you're reading through the Zoomdal text, to really focus on electroplating. Okay? Now, for AP, there is calculations associated with electrolysis. So one can calculate the amount of product made during electrolysis by using the following formula. You have coulombs is the amount of amps times seconds, and charge on 1 mole of electrons is 96,000 approximately coulombs. Now, in the AP formula sheet, you will see I is equal to Q over T. Okay, so I represents the current, Q is representing the charge, and T is the time in seconds. Okay, so let me go through an example question to show you how we go through this. Okay, so let's say, for example, it says an unknown metal is electrolyzed. It took 74.1 seconds for a current of 2.0 to plate out 0.107 grams of the metal from a solution containing MnO3 brackets 3. So what type of reaction is this? And the key word you can see is this. It says to plate. And notice you have an unknown metal with a metal ion solution. So in this case, what this particular reaction will be is electrolysis. Oh, sorry, electroplating. Okay. Now, so how do we approach this? So you could think of it like this. So the unknown metal nitrate broke apart to metal plus 3 and 3 nitrate minus 1. Now, and then the M plus 3 electrons will give you the M solid. Now, I'm not too worried whether or not it's oxidation or reduction. What I want to focus on is the mole ratio. So here, you take a look at the formula. So I is equal to Q over T. So what we have is we have Q is equal to current times time. So the current we know is 2.0 amps times 74.1 seconds. Okay, and that will give me a total charge of 148.1 coulombs of charge. Now, to find the number of moles, so the number of moles is equal to 148.1 coulombs divided by 9496485 coulombs. This is Faraday's constant. I think we talked about that in the Nernst equation. And so what we get here, if I take a look, do this in my calculator, I get 1.54 times 10 to the negative 3 moles of electrons. Now, notice the mole ratio is 1 to 3 to 1. So the amount of number of moles of M solid is equal to 1.54 times 10 to the negative 3 moles of electrons divided by 3. Again, because of the mole ratio. And then what we get is an answer of 5.12 times 10 to the negative 4 moles of M. Okay. And if we take the molar mass is equal to grams per mole, so that would be equal to 0.107 grams over 5.12 times 10 to the negative 4. And that will give me, let me see if I do this, 0.107 divided by 5.12 e to the negative 4. And I get an answer of about 208.9 grams per mole. And if we look on our periodic table around 2, this would be, it looks like about bismuth. Okay. Which is, take a look at my table. About 209, yeah, that would be bismuth. All right. All right, ladies and gentlemen, so that was the last little bit for electrolysis. Just something for you to consider, okay? So the key points out of here is you should understand what electroplating is, how do you set it up, along with how do you calculate how much can be produced using this I is equal to QT and Faraday's constant. All right, folks. Thank you very much. Have a good day. Bye-bye.